Phase equilibria is a really important topic in statistical mechanics. And there are a lot of areas of research, such as critical phenomena and other things, that relate to changes in phase. Not just the simple ones that we associate with, such as water changing to ice or water changing to steam, things of that nature, but phase, much more esoteric type phase changes. But we all start with some basic ideas about how phase changes work. When we do this, there are some things that I want to provide for you by means of sort of a vocabulary before we even start phase transitions. The topic is the difference between extensive quantities and intensive quantities. And so, in the case of extensive quantities, if I double the size of the system, I double that particular extensive quantity. Examples of that would be volume, number of particles, entropy, energy, Helmholtz free energy, Gibbs free energy, mass, enthalpy. On the other hand, there are other quantities in physics that are called intensive quantities that, regardless of the size of the system, you're not going to change the size of the quantity. That is to say, good examples, temperature, pressure, chemical potential, density. And it turns out that if you're dealing with these guys mathematically, if I take an extensive quantity and I multiply it by an intensive quantity, I always get another extensive quantity. If I take the ratio of two extensive quantities, I'll always get an intensive quantity. And so this is some background for what we're going to be talking about as we get into phase transitions. Let's give you some examples of phase transitions. Phase transitions generally incorporate some kind of discontinuous change in a quantity. So for example, let me give you a few. A solid to a liquid, the discontinuous change is in the shear strength of the material. A liquid to a gas is a discontinuous change in the density of the material. If I heat up a gas high enough to where it becomes electrically conducting, it becomes a plasma, now we're talking about a discontinuous change in electrical conductivity. If I take a substance that's a regular conductor at room temperature and I cool it to a very low temperature so that it becomes a superconductor, I'm also executing a discontinuous change in electrical conductivity. Or if I take a fluid and I decrease the temperature enough so that it enters the superfluid state, as liquid helium does, that discontinuous change is a loss in viscosity. So anytime we're talking about phase changes, we're talking about some type of discontinuous change in a physical property. And that's what we're going to do as we move ahead with this topic. We'd like to start with a working definition of the word phase in thermal physics. We'll use the one from Mandel, which says a phase is a homogeneous part of a system bounded by surfaces across which the properties change discontinuously. So there's that word again, discontinuous. Simplest terms, take our friend water. Water exists in three phases. A solid is ice, liquid water, and of course steam, or as water vapor. What we want to understand is what happens when two or three of these phases coexist simultaneously in equilibrium, and what happens when we convert from one phase to another? So, take a really simple example. Let's think about ice and water. When ice converts to water, there's no gradual change. It's either ice or it's water. The change is discontinuous. Same thing for water becoming steam. Ultimately, phase changes are going to be caused by attractive forces between particles in a system that forces the system into bound states, when I can add enough thermal energy or remove enough thermal energy. A nice way to study phase changes is to use what we call a phase diagram. And these are two good examples on the board. The first one is a real standard example for water. Typically when I do a phase diagram, I'm plotting two quantities against each other. Oftentimes it's pressure versus temperature. And we can look at this diagram and notice there are 2 points that are of real interest when we talk about phase diagrams. The first is a triple point. Triple point exists for water. It's at 0.06 atmospheres and 0.01 degrees Celsius. What happens there is water can coexist as a solid, a liquid, and a gas or a vapor at that point. That's the only point, the only temperature, pressure temperature point at which it can coexist in those three ways. We call that the triple point of a substance. Another area of real interest in research is critical phenomena. That is the following. If I continue to, at enough pressure and a high enough temperature, in this case 218 atmospheres of pressure, 374 degrees Celsius, we reach what we call a critical point. And at that point, you can't distinguish between the liquid and the vapor phase of water. Once water has reached that point, what we call a critical point. A great deal of research is being done on critical phenomena, has been being done for decades, and will continue to be done. You may notice in a diagram like this that while there are plenty of points, if I look at all these lines, there are points where two of the phases can coexist, plenty of them. There's only one point at which all three phases can coexist. Now, notice something interesting. This interface between the solid and liquid in water is very different than most other substances. For example, look at carbon dioxide. This interface between the solid and liquid, notice, has a positive slope to it. Water is unique in that it has a negative slope, which tells us that in this case, if I apply more and more and more pressure to ice, what will happen is that it becomes more and more solid. In the case of most other substances, when I apply more and more pressure, it tends to be more liquid. So you can see this, again, we have a nice example here of carbon dioxide. It has a triple point that's at minus 56.6 Celsius and 0.52 atmospheres of pressure. It has a critical point at 738 atmospheres and 31 degrees Celsius. Talk about phase transitions. I'd like to bring back something you probably learned in your first thermodynamics course, which was that of latent heat. So you might remember that as I heat a substance up, let's say I'm heating water from 20 degrees Celsius to 100 degrees Celsius, I can talk about the heat I have to add is equal to m times the mass of water times the specific heat of the water times the change in temperature. But you might remember too that once water reached a temperature of 100 degrees, we had a phase change taking place. It went from water to steam. At that time, to make the water convert to steam at 100 degrees Celsius, I had to supply some what we call a heat of vaporization. And that's enough heat to convert the phase. The temperature isn't changing at all during this time, but the substance, in the case water at 100 degrees, is converting from a liquid to a gas. And this is how much heat I have to add per kilogram. L sub V is the latent heat of vaporization. I have to add to cause that phase change. We call it a latent heat because it's not causing a temperature change. From the perspective of the first law, then I can write L sub V as the heat, and that's just going to be some change in energy plus some change in work that I would have to add. And if I want to do it at a molecular level, I might write it this way. LV is equal to some delta little e plus P delta V, where little e is the average energy per molecule, V is the volume per molecule. Typically, the pressure is constant in these situations, and so I can often write L sub V is equal to delta of E plus PV, which of course is my change in enthalpy. That's kind of interesting. So this is, latent heat is probably a really nice example where the enthalpy thermodynamic function is applied. In our last unit, we talked about chemical potential and diffusive equilibrium. And you might remember that we defined the chemical potential as minus T times ds dn at constant energy and volume. And we said if two systems A and B are in diffusive equilibrium, then it must be that their chemical potentials have to be equal. If they're not in diffusive equilibrium, the system with the larger chemical potential will lose particles to the system with the smaller chemical potential. And as we did earlier, we have written our thermodynamic identity with that added term, mu dn. We can also express the other thermodynamic potentials in much the same way. dF for the Helmholtz free energy, dG for the Gibbs free energy. The nice thing about this is it provides us with two alternate descriptions of chemical potential. I can write mu as the partial with respect to the of the Helmholtz free energy with respect to number of particles at constant temperature and volume. I can also write it in terms of the partial of the Gibbs free energy with respect to n at a constant temperature and pressure. And it's this latter expression, the Gibbs free energy, that's probably going to enter into our talk about phase transitions quite a bit more than will any other of the thermodynamic potentials. So let's talk about how Gibbs free energy and chemical potential affect phase transitions. So the Gibbs free energy for one single component phase is an extensive variable, and so it's proportional to the number of particles. So I can write Gibbs free energy as a function of T and P, and then of course the total number of particles. I can write that also, because it's extensive, as the total number of particles times the Gibbs free energy, temperature and pressure, and one particle. And I will define that as n times little g of T and P, where little g is the Gibbs free energy per particle. So what this is saying is if we're in diffusive equilibrium and the chemical potentials are the same between two systems, it also must be that the Gibbs free energy per particle will also be the same. So this is really nice, particularly if you're thinking in terms of experimental procedures, because if I can specify conditions so that two phases of a substance are in the same container, but I isolate them from the rest of the universe, if I can keep the temperatures and pressures identical, I should be it's very easy to see that I must minimize the Gibbs free energies per particle. It turns out that in the case of, suppose G1 corresponds to one phase and G2 corresponds to another phase, the same material, we can talk about these guys defining a curve in the same plane. So I could draw a phase diagram in this case, pressure versus temperature, and I can draw it like so, where here's phase one of a substance, maybe it's liquid, maybe it's solid, whatever, and here's phase two of a substance, different phase, and here are 2 points along the same phase curve. What this is saying is, let's say, suppose this is a liquid, and this is a vapor. We call this curve, this AB curve, a melting curve. I'm sorry, a vapor pressure curve. And so, this being the case, if I have diffusive equilibrium, G1 of T and P is equal to G2 of T and P at all points along this curve. Now, if there are 3 phases in equilibrium, such that you're at the triple point, that would be the intersection of 2 of those curves, and of course, the intersection of those two curves gives us a point in space. That's where, for example, when we talk about water, the substance, water and any other substance can only have one triple point. I'm going to add to this, I'm going to talk about deriving the Gibbs-Duhem relation. Suppose I have only a single species of molecule present. So the Gibbs free energy is going to be equal to the chemical potential times the number of molecules present. And the chemical potential is going to be a function of the intensive variables P and T. So we can take the total differential of the Gibbs free energy, and you'll get d mu dt delta T plus d mu dt delta P times n plus mu delta n. Let's compare this to what happens when we take the differential of the fundamental thermodynamic relation. Remember delta G we had written as minus S delta T plus V delta P. if we equate the two expressions, we immediately see that I can write my entropy as minus the derivative of the Gibbs free energy with respect to temperature at constant pressure and number of particles. I can write the volume as the derivative of the Gibbs free energy with respect to temperature at constant temperature and number of particles. And I can write the chemical potential as the derivative of the Gibbs free energy with respect to the number of particles at constant temperature and pressure. That being the case, it has to be that du dt is minus the entropy per molecule divided by n, or I should say minus the entropy divided by n, or we call little s, the entropy per molecule. The derivative of mu with respect to pressure is minus the volume divided by n, or what we call the volume per molecule. And so I can write that delta mu is equal to minus entropy per molecule delta T plus volume per molecule times delta P. This is what we call the Gibbs-Doom relation. And of course, entropy and volume are given per molecule or per particle. All these guys, by the way, S, V, and mu are intensive variables. So that's one very important relation that we want to remember. There's also another one that might be a little bit more useful in studying phase equilibria. And that's called the Clausius-Clapeyron equation. So suppose we'd like to compute the slope of a coexistence curve, such as a vapor pressure curve. We know that the liquid and vapor phases have to be equal at any point along the curve. So if they have to be equal at, let's say, suppose they're equal at some temperature A and pressure A, but they're also equal at some pressure B and temperature B. Let's let TB equal TA plus delta T. Let's let PB be equal to PA plus delta P. We can set the chemical potentials for the two phases equal at each point and subtract one equation from the other. If we do that, we'll get minus S vaporization delta T plus V for a vapor delta P is equal to, let's say we're doing liquid and gas, minus S for the liquid delta T plus V for the liquid delta P. So that being the case, so again, what we're doing, we've got pressure, and we've got temperature, and we've got this coexistence curve, and we have 2 points on the curve. Because they lie on the curve, the chemical potentials have to be equal everywhere on that curve. And so I can find then the ratio. I can take dP dt, and that's just going to be equal to the difference in the entropy of the vapor minus the entropy of the liquid divided by the volume of the vapor minus the volume of the liquid. This is one expression that we use for the Clausius-Clapeyron equation. We can also take the ratio delta P, delta T, take the limit as the 2 points approach each other, and we can get dP dt is equal to, again, the change in entropy for vapor and liquid divided by the change in volume of vapor and liquid. In the case where I can use the heat of vaporization as well, I can write this as the heat of vaporization divided by the temperature times the change in volume as well. So this is yet another expression for the Clausius-Clapeyron equation. We can do some examples of that. Let's do the following. We might ask the question, how much pressure would be required to lower the melting point of ice by 5 Celsius degrees? Tell you what, we'll pick that one up. Let's pick this one up in the next lecture.